Okay, thank you very much for your presentation. Now, we have a regional experience in reuse of the treated wastewater in 3 countries, Egypt, Tunisia, and Morocco. I would like to ask Dr. Professor Redouane Choukr to come and give his talk. Professor, please go ahead. I will read the bio. Professor Choukr holds a master's degree in agronomy from the Institute of Agronomy, Veterinary, Hassan II Rabat, Morocco, PhD Environmental Horticulture from the University of Minnesota, St. Paul, USA. He is horticulture, soil and water environmental expert with more than 35 years of experience in according and managing field-based projects and technical teams involved in the use of saline water and the use of pre-treated sewage in horticulture. As a senior level professor at the Institute of Agronomy and Veterinary, Hassan II since 1978. He served head of horticulture department from the period 1983 to 1996, head of salinity and plant nutrition laboratory since 1996. He has written numerous authoritative texts and books in the field of non-conventional water. Please go ahead. Thank you very much.
Thank you. Thank you. So I would like to thank the organizer for inviting me to give this talk today. This is a project, as has been already said, between Europe and also some northern African country, particularly Morocco, Tunisia, and Egypt. So let me give you some ideas about the project first. So it is this project. It's within the framework of Horizon 2020, and it started in 2016, and the duration is 4 years. The total cost is 4 million, and the European funding is around 3 million. The coordinator, who's supposed to be here presenting this project, is Dr. Dario Francesco from the University of Bologna in Italy. So to start with, So the general goal of this project is to develop an integrated set of technological and management instruments for enhancement of wastewater treatment, treated wastewater reuse, for irrigation and water efficiency in agriculture, with the final aim to increase the water security in selected hydrological basin in those 3 countries, which is Egypt, Morocco, and Tunisia. The selected basin in those 3 countries, it's one in the central of Morocco, in the Souss Massa Valley, and one in Tunisia in the north, in the Cap Bon, and in Egypt, we choose the northeastern Nile Delta. So the MAD4WATER consortium, the particular things is the key aspect of MAD4WATER is an intense exchange of know-how and researchers between Europe and North African country. As you can see, there is 18 partners from 11 countries, 13 research institutions, 4 small, medium enterprise from Europe, and an international organization, FAO, is also one of the partners, but also we have China as one of our partners. So the MAD4WATER project concept, it's based on 2 main pillars, which is the water supply, and wastewater treatment was selected as a source of water for subsequent reuse, and the water demand aspect, which is basically we choose the irrigation because 80 to 85% of the irrigated land in these three countries are used for of the water is used in those in the irrigation in those three countries. So the action related these two pillars are transversely characterized by two crucial concepts: adaptation, means of technological and management tools to the local condition of Tunisia, Egypt, and Morocco, but also an integration within each pillar between technological water management strategy, economic instruments, transversely between wastewater treatment and wastewater reuse irrigation. Just to clarify that we're trying to develop the best technological treatment for each site. We're trying to also develop the best technological irrigation system adapted to wastewater treatment, but also to develop the irrigation system adapted to this treated wastewater when we're reusing treated wastewater. So we have three phases in this project. The first phase was an analysis phase, which is development of tools to enhance the capacity to analyze water security in Tunisia, in Egypt, Morocco, as well as the impact of water security on food security and socioeconomic development. So as you can see here, for the analysis of water security was based on what we call the Asian Water Development Outlook. We focused in particular on economic water security, which according to this approach is evaluated on a scale from 1 to 20, which is the result of the sum of 4 index. And this, the first 3 index, 1 to 3, are the agriculture index. We have also the energy index and the industry index, which depend on water productivity and self-sufficiency of each sector. The last one, which is the 4th index, is the water resource index, which take into account several factors, such as rainfall, storage capacity, the level of water stress, drought duration, and the availability of reliable data. So this is some economic water of the current situation in this different country. You can see that both in all of the country, Morocco, Tunisia, Egypt, we have a low economic water security. Egypt have the lowest value, which is 11 out of 20, mainly due to low water productivity in agriculture and industrial sector and low self-sufficiency in agriculture sector. So this approach allows us the identification of the sector in which effort should be directed in order to maximize the overall level of the water security in a given country. So this is very important. So I'll give you water exploitation index situation in Tunisia, and from the study it shows by the projection of 2050, it indicates clearly an increase in water stress in the east coast in the northern part. So this will allow us to see where we can, I would say, develop where the wastewater could be reused and have a potential for reuse. So the potential of treated wastewater reuse in Tunisia, you can see that the analysis identified that the region which is significant contribution of treated reuse can be included in the strategy for water management in agriculture. And all the red ones are the area that shows the potential for the water reuse. And this could be done for each country. The second phase of the project was to develop what we call the technological phase. We have to develop both at the lab. We started with the lab scale development of technology of wastewater treatment and efficient wastewater reuse in agriculture in terms of irrigation system. So for both of Tunisia, Egypt, and Morocco. So then we have, after developing the lab, we try to scale up and validation of the selected technology in the 4 pilots of integrated wastewater treatment and wastewater reuse for irrigation that will be installed in these countries, which is Tunisia, Egypt, and Morocco. So this is, I'll show some of the technology that has been selected for municipal wastewater. This is for Tunisia. We use innovative nitrifying trickle filter system, followed by sedimentation, then a constructed wetland in order to eliminate some pharmaceutical metals that we detected in the raw wastewater. The second municipal wastewater was in the region of Agadir, where we're using first an anaerobic lagoon to reduce the BOD and nitrogen, followed by sand filtration, then a third treatment using UV in order to eliminate the bacteria to be used for irrigation. And for textile wastewater, we use a moving bed biological reactor to reuse BOD, nitrogen, and dye, then coagulation sedimentation to reduce the dyes, and absorption on the innovative resin to eliminate the dye that come in from the textile industry. And for a fruit packaging wastewater, we know that one of the major problems in treating wastewater from fruit packaging is fungicide that are used for treating the fruits before to be used for export. So we started with a flotation flocculation to reduce the fungicide and suspended solid, followed by an aerobic moving bed biological reactor, then absorption on the activated carbon to eliminate the fungicide. In the drainage canal water in Egypt, as you know, most of the large network of drainage canal collect a mixture of drainage water recycled from the irrigation field and untreated or sometimes partially treated municipal and industrial wastewater mixed together. Here we use a facultative lagoons to reduce the BOD, the phosphor suspended solid, followed by constructed wetland nitrogen to eliminate the BOD, nitrogen, and pathogens. In terms of irrigation technology, the project developed mini sprinkler adapted to hot climate and treated wastewater. The objective is to develop low-cost mini sprinklers, so to minimize the pathogen dissemination, and also to resist the potential clogging related to the use of treated wastewater and minimize water loss by evaporation. Another technology that has developed by Redouane industry in France is the calibrated nozzle for localized irrigation adapted to hot climate of treated wastewater. The objective is to develop what we call alternative a technology to alternative drip irrigation emitters capable of operating with treated wastewater with just a rough filtration of 1 millimeter size. So that means that we trying to prevent clogging using treated, but using this type of technology. This is characterized by a high discharge, and I think it's a mistake here. It's between 10 to 40 liters a minute that prevent any deposit in the emitter that may lead to clogging, to decrease distribution, unfortunately. But we use for irrigation, it's a low operation. We shoot a short cycle irrigation time to deliver the irrigation volume we want for the plant. We also, for Egypt, we modernization and increased efficiency of traditional surface irrigation in Egypt. Objective is to convert the open irrigation channels that are called here Mesquas and Marwas into optimized pressurized pipe that supply water to downstream gate pipe provided with calibrated nozzle that feed the field's furrows. The goal is to maintain a long-term and high water delivery efficiency and reduce drainage volume so as to improve water quality. Another technology that has been developed also with the Institute of Bari in Italy is plant promoting bacteria, growth promoting bacteria to enhance crop resistance to water scarcity. Here we selected some 5 bacteria which allow us, 4 of them have allowed us to increase the water stress performance of a crop. In this case is tomatoes, and we see that these 4 strains significantly increase water productivity, both in the case of fall irrigation as well in severe deficit irrigation system. And severe deficit irrigation, we use 50% of the requirement of the water that's needed by the crop. We also one package of the technology is a model for irrigation scheduling, especially adapted to the use of treated wastewater. Development of modeling tool capable of to identify the optimal water and nutrient application for crop irrigation in arid climate with treated wastewater based on the climatical condition, the key of the crop, the soil type, and so on and so forth, and climate conditions. So the approach for selecting all this technology that I talked about it. I talked about technology of treatment, talked about technology of irrigation used for treated wastewater, and so on and so forth. All this technology has been, and this is a very important part of the project, has been selected based on technical performance, on life cycle assessment, and cost-benefit analysis, but most importantly, it was based on the feedback from the stakeholder and on social and technical suitability for each basin level. Means that we presented all this technology to the local stakeholders in order to choose for sure the technology adapted for each one. So we have to have a score for all this. We did a SWOT analysis to define the characteristic of each pilot, location, type of wastewater, technology, and crop to be irrigated with. So if we're going to see the pilot plant of integrated wastewater treatment and irrigation was based on 2 sets, wastewater treatment technology, but also irrigation technology. So we made an integration between for each one. And in terms of the wastewater treatment selection, it was based on the performance, means that removal extent, removal rate, effluent concentration, maximum concentration. And in terms of irrigation and performance, it will be evaluated on the crop production yield, crop irrigation yield, and plant irrigation and fertilizer requirement. So this is the 4 MAD4WATER pilot plant that has been assigned after 2.5 years of work of selection, the technology and irrigation. And we're at the phase of upscaling at the level. In case of Tunisia, we're using municipal wastewater treatment by innovative tracheal filters and constructed wetland, and irrigation of wheat and corn by means of calibrated nozzle, micro sprinklers, and plant growth promoting bacteria. Also in Tunisia, we have another pilot using the textile wastewater treatment by the means of moving bed bioreactor and absorption on innovative irrigation of sorghum and triticale by means of calibrated nozzle and micro sprinklers. In Agadir, we're using municipal wastewater treated by anaerobic lagoon, sand filtration, and UV treatment, and we're irrigating olives trees by means of calibrated nozzles. And the last one, which is in Tunisia, it's in Lake Manzil, Egypt, drainage canal water treatment by means of lagoon and constructed wetland, irrigation of cotton and sugar beet by means of gate pipes. Give you some example of some technological performance that has been already done in the region in Egypt. You can see that high pollutant removal in terms of COD, BOD, total suspended solid, and total nitrogen, but also high, about 2.5 log removal of fecal coliforms. So the last phase, which is now will be done after we developed the performance at level of the treatment plant. There we have to look production of sustainable water management strategy for 3 hydrological basins, both Egypt, Morocco, and Tunisia, industrial exploitation activity, business for plan for the MAD4WATER small medium enterprise, capacity building activity, and policy recommendation. So in terms of the model that we're looking to develop, it's a hydrological agroeconomic model, which normally take into account the inputs and basically water parameters in terms of the availability of quality of irrigation, but also we take into account the farmer characteristic as well as the crop production cost, and come in with an output which is optimized cropping system, optimized mix of fresh water and treated wastewater, water productivity, but also socioeconomic output, which is the farm income and total food production as a labor required. So finally, the expected outcome of this project, it will be in terms of wastewater treatment technology, means that we hope by this is after 10 years of the project, means by the year 2030, we hope to produce, to increase the quality of 25% of the produced wastewater by using this technology that has been developed in the northern North African country, but also in terms of irrigation technology that allow us to reduce, to increase by 10% the irrigation land, but also increase the wastewater reuse in agriculture from 7% to 28%. But also we increase of available water by 3% of the water currently consumed in agriculture. And thank you very much for listening.